In our last video, we introduced the chi-square goodness of fit test and left off with the chi-square formula. In this video, we'll go through the steps for calculating a chi-square value and then determine the p-value and make our conclusions based on those results. Now, previously we were working on an example in which we wanted to see whether the number of students who attend hockey games is proportional to the number of students in each college at a university, or whether more students attended from some colleges and fewer attended from other colleges. Let's pick up where we left off. So here's our chi-square formula, right? We'll put it over there so that we have more room to work with here, right? And here are the observed values for the 200 students that we surveyed at the hockey game. Now, notice each person shows up in one and only one group, right? And the total across all four groups is 200. Now, let's list the proportion of students that we expect to see if the null hypothesis is true. These pi sub exp, that just stands for the expected proportion in the population. Now, based on those expected proportions, how many students would we expect to see? Well, we just need to convert the proportions to the number of students. That's pretty straightforward. We just multiply the total n of 200 by each proportion, right? And we get 0.5 times 200, or 100 students expected to be in LAS, right? And 0.15 times 200, or 30 students who are expected to be in education. And if we continue, we get 30 students who are expected to be in engineering and 40 students who are expected to be in NSFA. So at this point, kind of based on our observed and expected frequencies, let's calculate our chi-square. Now, first we'll start with the LAS group. That would be 105 observed, right? Minus the 100 expected. That difference squared divided by 100 expected, right? We then add in the education group. That would be 35 observed minus 30 expected. That difference squared divided by 30 expected, right? We then add in engineering. That would be 30 observed minus 30 expected. That difference squared, all divided by 30 expected. And finally, we add in the NSFA group. That would be 30 observed minus 40 expected. That difference squared, all divided by the 40 expected, right? If we solve each of those, we get our chi-square is equal to 0.250 plus 0.833 plus 0.000 plus 2.500. If we add all that up, we get our chi-square is equal to 3.583. Now, before moving on, let's take a closer look at the chi-square formula and how it works. Notice that the numerator is the observed number in each group minus the expected number in each group squared. So that's just the difference between what we observed relative to what we expected squared. Do you see how that's similar to what we were doing with z-tests and t-tests? We're just squaring it this time. And then look at the denominator. It's just the expected number in each group. So think about what that does. In a way, it just weighs that difference in the numerator by the size of the group. In essence, it adjusts for the fact that a difference of 10 people is relatively large if you only expected 20 people in a group, but it's hardly noticeable if you expected 20,000 people in a group. In fact, we see that very point in this example. Notice that both LAS and education had 5 more students than we expected. We observed 105 LAS students, but expected only 100. And we observed 35 education students, but expected only 30. Both groups had 5 extra students. But notice the impact on that value for our chi-square was greater for education. LAS, with its larger group, contributed only 0.250 to the chi-square, but education, which had the smaller group, contributes 0.833 to our chi-square. All right, pretty cool. Now also while we're here, you can ask yourself what happens to the chi-square if we observe exactly the number of cases that we expected to see. Well, we also see that situation in this example. Look at engineering. Notice we observed 30 students and we expected to see 30 students. 30 minus 30 is 0. 0 squared is 0, right? So engineering's contribution to the chi-square is 0. And think about it. If all of our groups had exactly the number of cases that we expected, then our chi-square would be equal to 0, right? And remember, that's the null hypothesis. The null hypothesis is that we'll see exactly the specific numbers that we expected. So if the null is true, we expect our chi-square to equal 0. Now, of course, just like all the other statistical tests, even if that population of students attending hockey games is exactly what we expected, we don't anticipate that our sample will be exactly what we expected. Random sampling variability will lead to some differences. But the larger the chi-square value, the more our groups don't have the expected number of cases. So again, just like all the other statistical tests, the question comes down to whether our chi-square is so large that the probability of getting a value that large or larger is just so unlikely, if the null is true, that we conclude the null probably isn't true, and we reject the null hypothesis. Now, to make that determination of whether our observed chi-square is big enough to reject the null, we need to look at the chi-square distribution. Now, by this point, it's probably no surprise that the shape of the chi-square distribution changes based on the degrees of freedom. But in this case, the degrees of freedom for the chi-square goodness of fit test is equal to the number of groups, or categories, minus 1. So notice, unlike the t-test where the degrees of freedom was based on the sample size, the chi-square degrees of freedom tells you nothing about how large or small the sample is. Therefore, you should include the sample size along with the degrees of freedom in parentheses when reporting your chi-square results. Now, thinking of this example, right, that we just calculated, we had 4 groups, right? So that means we would have 3 degrees of freedom, and we would report our chi-square value as chi-square, and in parentheses, 3, comma, n equals 200, our sample size, and those parentheses, equals 3.583, okay? So let's take a look at a chi-square distribution. Now, here's a chi-square distribution with 1 degree of freedom. This reflects a chi-square values that we would expect to see if we have two groups, right? 1 degree of freedom, two groups, right? And of course, if the null is true. In other words, if the values in the population are exactly what we expected, this reflects the range and frequency of chi-square values that we would randomly obtain due to sampling variation. Now, notice that it's only one-tailed. Chi-square values can't be negative in the same way that the F statistic can't be negative, right? It's based on squared values, right? It's the chi-squared, right? And just like Z and T and the F distribution, the more extreme the chi-square value, the less likely that you would have randomly stumbled on a sample giving you that big of a chi-square if the null were true. Now here, I'm adding in another chi-square distribution when we have 2 degrees of freedom or 3 groups. Notice that it's starting now to spread out a little more with the higher possible values because we're adding in results for an additional group when we're calculating our chi-square. And here's I've added a distribution for a chi-square with 3 degrees of freedom, or 4 groups, right? This shape where the probability distribution rapidly increases and then tapers off after that is kind of an illustration of what people will often use when describing or presenting an image of a classic chi-square pattern. Okay, and here's a chi-square distribution with 4 degrees of freedom, or based on 5 groups, right? Now, let's look more closely at the distribution based on our example that we've just calculated, right? We had 3 degrees of freedom, so here's a chi-square distribution with 3 degrees of freedom. Now, the first thing you may wonder is, what's our critical chi-square value? With an alpha of 0.05, what chi-square value do I need? What chi-square value is so extreme that only 5% of the time would we randomly get a value that large or larger if the null is true? What's that chi-square value where only 5% of the distribution is beyond that point and would result in us rejecting the null hypothesis? Well, if we look it up in a table or a calculator or Excel or something, we see that the critical chi-square value with an alpha of 0.05 and 3 degrees of freedom is 7.815. If chi-square is greater than 7.815, we'll reject the null. Only 5% of the time would we get a chi-square value that extreme or more if the null is true. And if the chi-square is less than 7.815, we're going to fail to reject the null hypothesis, right? In that case, it's less likely than our alpha level. We're going to fail to reject, right? So let's take a look at, for our example, what did we calculate? Well, we only got an observed chi-square of 3.583. So that means we're going to fail to reject the null, aren't we? We would have obtained a chi-square of 3.583 or more just too often. Well, more often than 5% of the time if the null were true. So we can't reject the null, right? But just how often would we have obtained a result this extreme or more if the null were true? Now, remember, that's our p-value, right? The area more extreme than our observed test statistic in the direction of the alternative hypothesis. That's this light shaded blue area, right? Well, if we look up the area that's more extreme than a chi-square of 3.583, with 3 degrees of freedom, we find that that area is equal to 0.310. Right? If the null is true and the values in the population are exactly what we expected, 31% of the time we would have nevertheless randomly ended up with a sample that gives us a chi-square of 3.583 or more. Right? Okay, so I think we're ready to wrap things up here. Let's first summarize our study and the results. Remember, we were interested in whether the number of students attending hockey games reflected the proportion of students across different colleges or whether they varied college to college. We set our alpha at 0.05, meaning that we're comfortable making a type 1 error and rejecting the null even when it's true 5% of the time. Our null hypothesis was that the proportion of students in the population attending hockey games was equal to the overall enrollment numbers I've kind of listed here, right? And our alternative hypothesis was that the proportion of students attending hockey games was not equal to that overall enrollment numbers, right? For this study, our sample consisted of 200 students attending a hockey game at the university. So what were our results? With an n of 200, we obtained a chi-square with 3 degrees of freedom equal to 3.583. Don't forget to include the degrees of freedom and the n in your parentheses, right? This gave us a p-value of 0.310. In other words, if the null is true, again, 31% of the time, we would have got a result this extreme or more extreme. That's pretty common. Because p is greater than our alpha of 0.05, our statistical conclusion is therefore that we will fail to reject the null hypothesis. In English, our substantive conclusion is that attendance at hockey games does appear to reflect the overall enrollment patterns across the colleges. Of course, there might be smaller differences that we just can't detect with a sample of 200 students. Maybe with a larger sample, we would see some differences. And that's why we don't accept the null, we just fail to reject the null. Okay? So with that, let's wrap up our discussion of the chi-square goodness of fit test. Right? Hope you found this informative. See you in the next video.